Hey guys, welcome. This is the 2025 AP Chemistry FRQ question number 2. My name is Mr. Kim. I'm an AP Chemistry teacher, and I am going to be going over this question. Number 2, answer the following question about ascorbic acid, which is vitamin C. A student combusts a sample of ascorbic acid to determine its chemical composition. The only product of the reaction are 0.2400 moles of carbon dioxide and 2.883 grams of water. A1, calculate the number of moles of water produced. That is actually deceptively easy. So let's just get it done and over with. I'm going to say A1. I'm going to go take care of that. And let's go over here. This is a long one, right? All right, so I'm going to go here and let's get started. I'm going to say 2A, right? Let's go to 2A and I have my notes here. All right, 2A1, right? Yeah. So what do we got? We got 2.883 grams of water, right? And that's easy, right? Because all we need is the molar mass of water, and it's 1.008. That's for hydrogen, and then oxygen is 16 according to the reference table. So that gives you a total of 18.016 grams per mole of H2O. And that's it, we're done, right? That gives us 0.1600, right? Uh, for sig figs moles. So the answer that I'm going to put down is 0.1600 moles of H2O produced. Okay, and let's go to Roman numeral 2 right here, and let's take a look at what that question is. Okay, Roman numeral 2 said, we are. The mole ratio of carbon to oxygen is 1:1 in ascorbic acid. Um, okay, based on this information and your answer to part A, which is the number of moles of H2O, determine the empirical formula of the ascorbic acid. All right, so let's think about this. So carbon to oxygen is 1:1. We got to go back over to look at the combustion of ascorbic acid, right? So if we look at the combustion of ascorbic acid, what do we know? We know that it's this plus O2. I don't know if I wrote it down when I was solving this. I didn't. So it's this plus O2, right? So it's CHOXYZ plus O2 giving us CO2 plus H2O. Now, we don't know the coefficients yet, but we do know that the entire source of carbon comes from, and then we know the carbon, right? Because we know the 2400, 0.2400 moles of CO2. So we know that all of this came from here, right? And then what else we know? We know that this, which turned out to be 0.1600, right? Oxygen is all over the place, and we know this is the O2 is in excess, so that oxygen is not useful. But we know that 0.1600 of H2O allows us to figure out how much hydrogen we have, which is completely from the ascorbic acid. And that makes this easy because they said the carbon and oxygen is 1:1 ratio. So therefore, once we figure out the carbon, we figure out the oxygen, and we're good to go. So let's go solve this. All right. So going over here, all right. So let's take a look. Um, so let's look at moles of CO2, right? That came out to what? 0.2400 moles, right? But what do you know? That's the total number of moles of carbon in the reaction, right? Total in CXHYZ, HY H, something like that, right? Who cares? All right, so we know that, and then we got the water, right? We got 0.1600 moles of H2O, but we're interested in the H, right? So therefore, we're going to have to do a little bit of conversion here where we know that in 1 mole of water, we got 2 moles of H, right? So that gives us 0.32 moles, right, of H, right? And what else we know? We know that this is the same as the number of moles of carbon and oxygen. So we know that this both O and C. Now we're done. All we have to do is do your empirical formula, which is going to be, you got your C, H, and O, and what are the number of moles? Let's take a look. So we know that carbon and oxygen is 0.2400, right? And then what else? The hydrogen is 0.3200. And you remember the empirical formula rep, percent to mass, mass to mole, divide by small. So we're at mole, so we're going to divide by small. The smallest mole is 0.2400, right? And what happens? So this is going to come out to 1, and this one comes out to 1.33. Okay, so again, percent to mass, that's the first line, mass to mole, and then divide by small, we just did that, and then multiply until whole. So in order to get a whole number, we're going to have to multiply all of these guys by 3. That gives us 3. And what's that? That's 3.99, which is 4, and this is 3. So our empirical formula is going to be C3H4O3. So I'm going to write C3H4O3, circle it for the readers, and we are done. And we're feeling good about this, right? You feeling good about this? I'm feeling good about this, okay? So that's done. Let's keep going. Ascorbic acid acts as a weak acid and shown in the equation. The following titration curve was produced when 10 mil sample of ascorbic acid was titrated using sodium hydroxide. All right, good to know. Calculate the molar concentration of ascorbic acid solution. Well, that's actually quite easy, right? Because what does that mean? We need this, which is going to be what? Volume of our base, right? We got your molarity of the base. And what else? We got our volume of the acid, and we're trying to solve for the molar concentration, right? Which is Ma. So let's go. So I'm going to go over here and um, I'm going to set up 2B. I believe that's 2B, right? That's right. So I'm going to go, do I have enough space? Yes, I do. I'm going to go 2B. And let's put up some shopping list. It's MAVA, MAVA, MUVUB, right? And we're trying to solve for this. And then what are some values here? Our VA was 10.0 milliliters. Molarity of the base, I believe, was 0.0550 molar. And the volume of the base used at the endpoint was 16.0 milliliters, right? All right, so we know that it's MAVA equals MUVUB, and we're solving for MA. So it's going to be MB times VB over VA, and we plug our values in. 0.0550, right, times our VB is 16.0 milliliters all over 10.0 milliliters. Okay, and that brings up 0.0880 molar. So I'm going to write over here. I'm going to write, what am I writing? Concentration of the HASC is equal to 0.0880 molar with a box around it, and we are done. Let's go to BI2. All right, BI1 is done. Let's look at BI2. From the titration curve, determine the approximate pK of ascorbic acid. I don't know about you, but as an APChem teacher, I've been drilling this into my students. On a weak acid, what do we know? pKa is equal to pH at the what point? Halfway to equivalence point, right? So equivalence point is 16, so therefore halfway point would be 8. And if you go to 8, this is the halfway point, and here our pH would be exactly equal to the pKa. So let's see what this is. I got, oh, excuse me. I just didn't like that. Stupid computer. Okay, so that's 4 right here. That's 6. I believe that's 6, right? Yeah. It's no, it's 4 and a 5. So this is a 4, that's a 5, that's 4.5. I would say 1, 2, 3, 4. I would say it's around 4.15 or 4.2, right? So let's call it 4.15, right? You want to call it 4.15? Or you want to call it 4.2? Let's call it 4.2, okay? My guess is that the answer will be between 4.1 and 4.2, okay? So let's go. So 2B II, let's solve it over here. 2B II, okay? So what do we know? pKa equals 4.2, and you should double check because I know in previous years they said explain how you know, but in this case they didn't say explain, so I'm just going to move on with my life. So 2B III, what do we got going here? In that one, let's see. What is the value of the ratio of the let's see, of the base over the acid when the pH of the solution 4.7. Hey, do you guys know what we're talking about? As my students will say, David Hasselhoff or Henderson Hasselbach is in the house, right? So let's go over here, and so this is going to be easy. So my students, right, I told them, right, because we worked with a lot of Henderson Hasselbach, or as they say, David Hasselhoff, right? I say, this is my jam, right? Why is that? Makes you feel like you know what you're doing, all right? We know what we're doing, okay? So go over here, right? So what are we solving for? We're solving for the concentration of our conjugate base, which is ASE minus, over HASC, right? Not E, can't see. All right, that's what I'm going to look for. All right, so let's do this. So we know that the Henderson-Hasselbalch is pH is equal to pKa plus log of base over acid, right? Or in this case, it's ASC, which is our conjugate base, over acid, right? All right, so what do we got going here? We got pH in the problem said, what if it's pH 4.7? We got that. We got our pKa. Our pKa, at least the way I called it, is 4.2 or 4.1, depends on your what you want to call it. So it's going to be log of ASC minus over HASC. Okay. So moving the term onto the other side, you're going to get a log. Come on, can I get some writing here, please? We're going to get log of ASC minus over HASC, which is going to be equal to 4.7 minus 4.2, which gives us 0.5, right? So you're going to take the anti-log of both sides, which is going to make the log drop out on this side, right? And how do you take the anti-log? It's 10 raised to 0.5 because we're talking base 10 logarithmics, right? So what does that come out to? If you put that in, I believe you get a value of 3, right? So I'm going to put in 3 over here. Like I said, if you picked 4.2 for pKa, your value might be different. What are you going to end up with? You're probably going to end up something a little bit higher, probably like 4 or something like that, okay? It wouldn't matter because, like I said, on the pKa, there's going to be probably some range they're going to accept. It's going to be anywhere between 4.1 through 4.3, maybe they'll take, which means that when they do that, these values for BIII will also change as well, but no worries. Okay, that's fun, right? That is our jam. My students are sighing right now. All right, so that's done. So let's go to letter C. Dihydroascorbic acid, DHASC, can be produced by reacting ascorbic acid with the triiodide ion as represented by the following equation. The student runs 3 trials of the reaction with 3 different initial concentration of HAC and I minus 3, producing the following data. The rate law for the reaction is rate equals K, blah, blah, blah. It's, as you can see, this is first order in respect to both of these. Overall, it's a second order, but we're not going to talk about that right now. Explain how the data in the table support the conclusion that the reaction is first order in respect to HASC. All right, to solve this, right, we're only looking at this one. So don't go crazy solving for the whole thing, all right? So let's go to CI. To solve this, we're going to look at that. So what do? It's going to be what? Rate is equal to K, and then what we're going to do is HASC raised to m because we technically don't know what the rate order is, and it's going to be triiodide like that, right? All right, so how do we do this? Remember, in order to figure out the rate, what you do is you isolate one of the species that you don't want to care about. So, which means that we're going to pick up 2 experiments where the triiodide is going to be held constant, which is these 2 guys, right? And then what else are we going to do? You could do trial 1 over trial 3, but I like to do trial 3 over 1 because I don't like fractions. And if you do trial 3 over 1, you notice right here that it's going to be 5 over 2.5, which is going to be 2, right? So with that in mind, let's go and solve this problem. Okay, explain. Okay, let's go. So we're trying to solve for the M value, right? Or for the HASC, right? So that's gonna be 2CI. Do I have space here? Do you think I have space here? I got space here, right? Of course, in class, I tell my students, put some space, right? Don't cram it all in, but here I am cramming it all in. All right, so we said we're going to use trial 3 and trial 1. So we're going to say, so it says to solve for it, to justify, right? So let's just solve for it, and then let's see. In fact, you know what? I'm sorry. I'm going to go back for a second. I'm going to see what they're asking us to do for a second again, because if they're asking us to justify, right? Then I'm just going to solve it, right? Rate law for the explain how the data on the table support the conclusion that, all right, so you just have to solve it, right? That's the best way to do it, I think. Or you can just do it in English too, but I'm just going to solve it, okay? So when you have that, what do we got? We got trial. I said we're going to use trial 3 over trial 1, right? Which means that it's the rate. Do I have the rate? It's 4.914 times 10 to the minus 4, right? Divided by 2.4 something, right? 457 times 10 to the minus 4. Okay, so these are our rates, right? And right away, I could actually do this math and then come out with a perfect 2-to-1 ratio, right? And then what else? We have our the rest of the expression, which is k, right? And times the what do we got? We got our the acid, which is going to be 0.900 raised to m over 0.450, right? Raised to m, right? Remember, so it's rate is equal to k times the concentration of our first guy raised to its rate order, and then times the concentration of the second guy, which is in this case in trial 3 and 1, they're both 1.200, right? And because of that, even though we don't know what the n is, it wouldn't matter because these two cancel out, that two cancel out. And remember 0.9 over 0.45, that's also 2 over 1. So now we got a 2 over 1 is equal to 2 raised to the m over 2 raised, I'm sorry, over 1 raised to the m, right? Got too excited. And what do we know about this? We know that m is first order, right? So I don't know if we need to actually explain it. I think this is more than enough, right? I'm just gonna write using trials 3 and 1, we change concentration of HASC, I think that's it, right? By 2x, leaving, who's the other guy? Triadi, right? I3 minus constant. And can see the rate has doubled. Hence, first order. Here we go, just like that. Okay. All right, so that's CI, and let's go to CII. What is that? Okay, pause. Okay, CI was done. Let's go to 2. Calculate the value of the rate constant K for the reaction. Include your units. This is so easy, right? So what happens, I usually tell my students, stick to the middle one, right? Or unless you see a value that is really easy to plug in, stick to the middle one, right? So let's stick to the middle one and plug these values in. So for C2, we got space. No, I'm gonna use my own advice to my students. They're gonna laugh at me. 2C2 right here. What are we solving for? We're solving for the rate constant K. So I'm gonna leave a space over there. So let's write out our expression. Rate is equal to K, right? HASC and our triiodide, right? Am I right? I'm right. So now we're going to solve for K. I actually like to do this where K is equal to rate over, set up your equation before you plug in. Why? I'm going to tell you in a second. Okay, so you do that. And let's plug our values in, shall we? So if you go back to the chart and plug in values for trial number 2, the rate was 1.229 times 10 to the minus 4. And that's going to be what? Molar per second. That was the unit of the rate law. And then you got this. And then what do you have in the bottom? You got 0.450 molar for the bottom for the HAC. And for the iodate, you got 0.600 molar. Okay. All right, so what do we get? So plugging this in calculator, you should get a K value of, I hope I'm right, 4.55 times 10 to the minus 4. Now, this is where I said I like setting this up because now let's say take a look at the units, right? We know that the molarity on the top cancels out the molarity on the bottom, okay? So therefore, what do we end up with? We end up with 1 over S, 1 over M, right? So our unit is going to be, why are we not writing? M to the minus 1, second to the minus 1, and that should be our unit. Also, you could, or the unit could also be, right, liters per mole times second. That could be the unit as well. So I'm going to go up here, right, 4.55 times 10 to the minus 4, right? I am going to use this because my textbook, which is Zumdo, I think likes to use this, liters times mole minus 1 times seconds minus 1, right? Now remember, this unit and that unit and that unit, it's all the same, okay? It doesn't matter which one you use. Okay, so that's C, 2II. Let's go to D. D is right here, all right? So 2II, and we're excited. Why are we excited? Because we're into 20 points already, right? The triiodide ion I3 minus is significantly more soluble in water than elemental iodine. It is. Identify an intermolecular force between I3 minus and water that is not present between I2 and water, which could explain the difference. Okay, so let's take it. First of all, what do we know? Everything has LDF. I have LDF, you have LDF, right? Grandma has LDF, right? We all have LDF, right? So what else? This is I2. This is a nonpolar covalent, right? So therefore, this is the only thing it has, right? It doesn't have dipole because it is not a dipole and it's not an ion. What do we know over here? Well, we want to write dipole, right? However, this isn't a dipole, right? Why? Because what's that? That's an ion, right? And what are we interacting with? We're interacting with water, right? Now, it wouldn't be making hydrogen bonding, would it? Because in order for it to form a hydrogen bond, you need a hydrogen on this one with a what? Nitrogen, oxygen, or fluoride, right? And you don't have one of those. Or conversely, you would need a lone pair of the F or N that's attached to hydrogen. Again, we don't have that. So there's no hydrogen bonding happening here today. So what do we got going? You've got an ion to water, which is polar, which is dipole. So this would be an ion-dipole interaction, right? Not a dipole-dipole interaction. So we are done. So you know what? In fact, I'm so confident. I'm going to cross that out, be done with number 2, and slide over here, right? And it said identify what has, right? So I'm going to write 2D, right? And what am I going to say? I'm going to say triiodide has an ion dipole interaction. Okay. With water, whereas diiodine, right? The diiodine has only London dispersion forces. It being a nonpolar covalent molecule. Okay, and we are done with number 2. I hope this was helpful. So thank you for watching.